Good morning, ladies and gentlemen. I would like to welcome you to this session. I hope you had already some sunshine and coffee this morning. If I just look to this, it's not really the 50-50, let's say, distribution between female and male. So I think probably we have to work in nanomedicine on that to have some more ladies here. Anyway, thank you for coming by. The title this morning, let's say for the session, is New Measurements, Techniques and Standards to Meet the Need of Medicine. And I probably just turn the word to you. You explained already to me that you're giving more a scientific talk than really, let's say, a talk on only the measurement. But feel free, I think probably quite interesting. Thank you very much.
So I might be mildly controversial, but that's a good thing, because otherwise it's a bit early to be sitting there getting bored. So I'm really going to talk more about what I think are the nanomeasurement requirements for nanomedicine rather than what we do as a company and our technology. If you want to find about technology, then come and see us or look up our website. I was at the ICEV extracellular vesicle meeting a few weeks ago, and Francis Collins spoke at that, and I think it's related to this field, about the need for rigour and reproducibility, and particularly when you want to be funded by US government who actually want some medical benefit to come out of it all. And he made the point that the very, very high number of papers that are published that are not actually reproducible. And I think nanomedicine has exactly the same problem. Everybody gets a bit carried away. We're going to cure 100,000 people of cancer, but in the meantime, we can't do a simple thing like measure our particles properly. So in terms of the measurement context, this is where I get a bit controversial. Nanomedicine measurement, I'm going to say, this clearly lacks precision and repeatability. Most of it is just plain garbage and embarrassing. There's a bit of complexity with nanoparticle constructs, but they're really not that hard to measure properly, but everybody's still living in the 1990s. DLS is completely unsuited, so about 90% of the papers that you see have their DLS cartoon. What's the point? It's really just a waste of time. So for medical adoption, the field needs to adopt accurate, repeatable, verifiable data. Traceable data, a real measurement, not a cartoon. So in terms of the translational context, what we're doing is high precision nanoengineering. I used to be a civil engineer. I build bridges, airports and hydroelectric projects. So you're doing that at a mega scale. Nanoengineering is really no different. You're just doing precise measurement. You're just dividing the meters by a billion to get to nanometers. You require precise measurement to do precise nanoengineering. QA, QC by accurate characterization is quite practical and achievable, generally not done. Now, mainly the regulatory regime is to have a huge amount of detail around manufacture. So we had a talk about regulatory issues on Monday, and the inventor of Abraxane was there and was asked, what happens if you change your albumin supplier? You know, that was when Lay asked that question. You know, and all of a sudden, well, does that throw out your whole approval? Well, if you could measure the output properly, if you measured what you're making, it wouldn't matter. You know, and that's just not done. And to me, it's a huge waste of time and effort and to not very good results. So I think I'm going to make that statement in bold. We need to reinvent nanomedicine measurement. This is a paper, an extract from a paper that was published about 3 years ago showing the four main particle measurement techniques measuring a trimodal sample. I don't know if it's got a pointer on it. At the top, is this a pointer? Oh yeah, maybe, yeah. So these are three monodispersed particles mixed together. So everyone can measure the monodispersed particle set. That's a trivial problem. But what happens when you mix them together? So DLS, this is the most common form of measurement, is measurement. Sorry, that measurement is just garbage. It's a waste of time. There is no link from that measurement back to what you measured. You cannot get a one-to-one relationship. So you get that data, what does it mean? Unless you tell it, unless you really know what it means, it's useless. But that's what everybody does. Why do they do that? I'm not sure. With NTA, you get a better result than that, but same thing, hasn't got the resolution. You might tell it it's 3 and get some wavy lines, but not precise. Disk centrifuge, you can at least clearly see there are 3. But with TRPS, you can see the 3 in proportion. So the point of this is that you need a one-to-one relationship between the data from the measurement and what you're measuring. If you don't have that, then when you get the data, how do you know what it was that you measured? Unless you already knew. And that's kind of pointless. That's just a circular argument. So what is it that you can measure? So for the purposes of this talk, I'm talking about particle concentration. People see that as just counting, just a number, and I'm going to talk about it in a minute. It's particle size. Typical particle size is a Z average and a PDI. Again, complete waste of time. The PDI is a meaningless number. So you need the real size-based distribution, not a made-up cartoon. Particle electrophoretic mobility, you'll note I didn't say Zeta potential, and charge distribution. So particle by particle charge, so you want the distribution of charge as well as the overall average. Calibration is really important. So if you want traceability, you want to do measurements in Holland, and then another measurement in America, and another measurement in Australia. You all want them to mean the same thing. So calibration allows traceability, standardization. We're doing this in the extracellular vesicle field, and there's a lot of work with metrology institutes around this work. Does that happen in nanomedicine? No. This is just showing you really how it can be measured. It's not the only way, but it's one way. TRPS is tunable resistor pulse sensing. It's the Coulter principle driven down to the nanoscale. It's tunable because you can tune the size of the hole, but most importantly, you can tune the driving forces through the hole, control the speed of the particle, and then measure the different things. So you can measure the particle volume accurately, you can measure the particle electrophoretic mobility by looking at the time through the hole, and you can measure the particle concentration by how frequently particles go through the hole. So moving on to concentration, this is a very important point in my opinion. The particle concentration is a fundamental data point. All these percentages versus size are really garbage, because you could have 1%, 20%, 50%, 100% of a real number, and you never know which. So I think you need to pull everything back with particle concentration. How many particles do you actually have? It's really basic, but nobody does it. We've moved on from a single number, C for concentration, so instead of a single number 10 to the 9 per mil or something, we've now realised that with polydispersed systems, which most things are, you need to define the size range. And this became obvious in the vesicle world, where different people were coming up with different numbers, and we could see they were all just measuring a slightly different size range. So merely by specifying the size range, you standardise things much better. So we've established this notation, and quite a few people are using it now, of the concentration C, 70 to 30, means the concentration between 70 and 300. It's kind of a basic thing, but it just applies a little bit more discipline to the notion that you're measuring every single particle, which is normally not the case. So this is the sort of thing you end up with. You can have, you see the number on the y-axis versus the size, and if you don't have a size restriction, the number you get is 1.4 times 10 to the 10. If you're really looking at the 70 to 80, you get a different number. So it's not that one number is right or wrong. You just have to be quite clear and specific about what you're giving to people. We did a project on extracellular vesicles, but it applies to nanomedicine. It was called the Gold Standard Projects. There were 4 universities in Europe, Duke in the US and Melbourne in Australia, all given the same frozen plasma. They had to extract the vesicles and measure the concentration. The idea being, well, how far out of would they be? And that was all presented at IZON, but it was, the project was designed to show that you could standardise results, and that 6 people, different groups around the world, would actually get the same answer, which is normally not the case. This is just showing size, so I went through concentration. The preferred approach, in my opinion, is not either. It's actually showing the 2-dimensional plot. So this is just an example of liposomes frozen and thawed. So you have your specified method of manufacture. You've made the liposomes, which is the green, and then someone's gone and frozen them, presumably it's all been approved. But then we're measuring in some detail what comes out afterwards is quite different. If you don't have the number in there, then it's pretty hard to do that accurate comparison. And if you filter particles, it's the same. You need the number of particles going in and the number coming out, and then you can do an accurate comparison of what happened. It's really quite simple, but this is much more detailed, much more useful data than the wavy line that you get out of a DLS. This is for extracellular vesicles, but this is the kind of high resolution comparison. So in the case of generic copies, we had some talks on Monday about, is a copy the same? If you come up with enough detail, you can see that. So this is an Alzheimer's disease sample, the AD versus the control in brain-derived vesicles, but you know, you're looking at that level of detail. The wavy line doesn't help. Moving on to charge, so you can actually measure electrophoretic mobility particle by particle. I won't go into the detail of how you do it, but because we haven't got time, but it can be done quite simply. Where is it useful? Most people want to talk about Zeta Potential. There's this our view is that there's an artificial construct It's meaningful in a few specific cases. It's a bit like measuring monodispersed particles, but in most cases it's not meaningful. As I understand it, you cannot have a zeta potential for a metal particle, yet everybody gives you one. Where you have particles with DNA constructs and the like hanging off them, which we often do, then your DNA is hanging out into this kind of zone. What does that mean? In our opinion, it ceases to mean anything. So we've been doing studies of work where we're adding DNA to nanoparticles, measuring the charge, hybridizing more DNA, making the DNA longer, that kind of thing, and studying that in some detail to try and work out what all this means. And you quickly realize that zeta potential is not the best way to describe charge. What you're measuring is electrophoretic mobility, and what you probably want to know is how the particle is going to interact with the bio, and what about aggregation. This is just showing if you mix two particle types together, the PALS is the DLS, so you've got a 15 and a 40. When you mix together on PALS, you get the average 25. When you do this with TRPS, you can see that actually when you overlay them, the blue was done separately, the red were together. You can then differentiate these particle sets. Again, not terribly difficult, but it gives you some useful information. If you're developing new systems or you've got particles mixed up with bioparticles, you can start to unwind what you're doing and get some real data. This is the kind of plot you can achieve if you want. This is functionalizing liposome, so there's a whole lot of areas around this where you're adding PEG and the like, and then you can see how that's been achieved across the set. So just focusing back onto reinventing measurement, we've got 30 seconds to go. Concentration, it needs to be done, which I think should be obvious, but it needs to be defined with the size range unless your particle is very monodispersed. The size distribution needs to have the particle number, not percentage. Zeta potential is misleading and ought to be replaced by electrophoretic mobility or another agreed index for aggregation. And can we have real measurements, please, not cartoons? That's me. Thank you.
Thank you very much. I mean, you made the statement we have to reinvent nanomedicine.
No, measurement.
That's the measurement,
Yes.
let's say, okay. So any question to Hans on his, let's say, presentation? I would like to ask you a question on the regulatory part.
Yes.
So how do you see that will develop? Because that for really bring it into the market, let's say, and for diagnostic use or whatever, I think regulatory is a very important issue. So how do you see that will develop in the future?
We had some discussions with FDA. We're having some with EMA. We've got a project with NCL at the National Cancer Institute, National Physical Laboratory. So a lot of the metrology institutes are really interested in traceability, and one of the areas of difficulty is traceability of concentration measurement. There isn't actually a traceable standard. We make our own. So I think we need to demonstrate traceability in a metrological way and then show to the regulators how this benefits the field. It makes life easier for them, actually makes life easier for companies, speeds up the use of the nanomedicine, which is what they all want, I think. But I think everybody just needs to get out of their 1995 mindset and get rid of their grungy clothes and move into 2015. I don't think they quite realise how easy some of these things are now.
If you would do your best guess, what do you think how long it will take that that there are regulations?
Well, I think even if the regulators just put out a little note saying, well, we would prefer to see a number-based distribution, and by the way, the concentration of your particles is quite important. That would then get the field to quickly shift, because I met someone the other day who said, well, the FDA doesn't want it, we're not going to do it. You talk to the FDA, well, the companies give us the data and we don't tell them what to do. So that's kind of stupid. I think someone needs to say, well, actually, even write a little note, it would be preferred if this was the way you did it. And I think that would get the companies to switch. And once they switch, they would realise actually our life would be a lot easier, not a lot harder.
Any comment from any of the other companies? Oh yeah, could you please use the microphone? Would be nice. It's just next to you.
I can hear you, yeah.
Oh, okay. I would like to make a comment on Zeta Potential. You're right. Combined with Zeta Potential, you should know the degree of aggregation or agglomeration. But you should also do a titration against the environment, because the Zeta Potential is very sensitive on the environment, And to measure zeta potential only at one condition does not tell you
Correct.
everything about your sample.
Absolutely, that's correct. But it wasn't the point about electrolyte concentration changes it. The point is that zeta potential is derived via an equation from the electrophoretic mobility. So the electrophoretic mobility is the thing that's measured and is artificially converted to zeta potential. So they both change with different electrolytes, you're quite right, if you increase the salt conditions. So if you measure the charge in deionized water and want to use it as a nanomedicine, then the charge will be wildly less in the high salt conditions. That's correct. But my point was zeta potential, people are used to the number, it's a meaningless number. That's my point.
Okay, thank you.
Thank you.
Okay,
Thanks.
thank you very much, Hans. So our next speaker is Dr. Clemens Helbrecht, and he will present us